Very good afternoon, everyone. So there was some technical glitch on my side, and because of that video recording got stopped. So I will record certain extent, and then will merge with the remaining part. So the in this week two, the content, like lot of things we have covered, and the assignments is also there for you guys to solve it. And if you face any doubt, any problem in solving those things, please let me know. We'll have a discussion on that. You can always comment on the you can always put a comment on the discussion forum, or you can also put the comment on this particular video itself on the comment box. Will i will uh, it would be grateful for me to reply to that. So let's see the content that has been covered in this week, and they are as follow. So we discussed about the mirror indices, we discussed about the plane, and we also discussed about the direction. what are the what are the things that has been like in the direction. While do, we have to write the mirror indices, there are the particular steps. In that step we saw that, okay, first we have to take the origin, and origin we have to take onto the direction itself, right? So then second step we saw, okay, we have to, along the a, b and c, we have to find what are the intercept the second point is making, that we have to do. Then we'll put it in the parenthesis. Okay. And then after that, what we will do is that we will reduce it to the smallest integer possible, and if something is negative, then we'll put it the bar. Like, we will not write 1 minus 1 1. If the direction is 1 minus 1 1, then we'll not write it like this, we'll write it like 1 1 bar 1. This is how we will write for the direction. In the second case of the plane, we have saw that, okay, like for the direction we choose the origin onto the direction itself, while for the plane we will choose the origin onto the plane. Sorry, it should not be onto the plane. So the origin should not be on the plane. While for the direction, it was supposed to be, it must that it should lie onto the direction itself. So this is a major difference. And again, we have to take the reciprocal and all in the plane case, which was not supposed to be done in the direction. So we have discussed these things. Then we discussed about the y zone law, where we have saw that, okay, we are having the HKL, if this is a plane we are having, and we are having the U, V, W, this is the direction we are having. So if the direction is parallel to the plane, or it is lying onto the plane, then in that case what we will get, U times of H plus V times of K plus W times of L will be equal to 0. We know that. We know this part. So this is a y zone law. We saw its application also, that we can find the common direction between any two plane. We can find that, okay, whether the particular direction is lying onto the plane, or it's parallel to the plane or not. Those things. There are the multiple applications. These are the few of the application which we are going to solve questions on that, and which we also discuss the theory in the class. Then next we found about the interplanar spacing, and for the orthorhombic crystal system we have saw that these are interplanar spacing. Then we can write that it will be h square plus a square k square over b square plus l square over c square. This is for the orthorhombic. We know that a, b and c are different. For the cubic, you can say that for all of them it will be the a will be the common, and then you can write d will be equal to the a root over h square plus k square plus l square, right? And that's how we have studied about the interplanar spacing. That is a distance between the two consecutive parallel planes. Then we learn about the Bragg's law and lambda equal to 2d sine theta. That is a mathematical form. We have learned about it, and we have also learned the one of the major part which says that, okay, the diffraction you can think of as a reflection, and that's what the one of the also, which is not very famous, but it's very fruitful. It's very important to understand, to keep it in mind. Then we learn about the close packing of the hard sphere. We learn about hexagonal close pack. We learn about the cubic close pack, FCC, those things. Okay, we know that, okay, the highest packing fraction which we can get in the 3 dimension, if we have to stack a sphere, it will be 74% itself. It won't be more than that. So these are the list of the things that has been covered in the class. If you feel any doubt in them, if you want to discuss anything, please comment on this particular video, or you can also put it on the doubt solving forum. Let's move to the questions. The first one. Here we can see that the Miller indices of the direction. What type of the bracket we will use for a direction? A direction, one direction. We are not talking about the family, only one. So in that case, we are aware that okay, we will use the square brackets. While if there is a family of the plane, sorry, family of the direction, then we will use this. This is for the family. This is for one single person, one single direction. So the option B is the right answer over here. Right. Let's move to the next part, next question, question number 2. What is the Miller indices notation for the direction along the y-axis? Okay, so we have to find the direction which is along the y-axis. We have to find its Miller indices. Let's make a cube. Since it's not specify anything, I can make a cube. I can make a tetrahedron. I can make a triclinic, orthorhombic, anything. So this is y, x, and let's say this is the z-axis. R direction is along the y-axis, so let us say this is the direction which we are talking about. So again we have to, okay, this is the direction. If it's not visible, starting from the tail is over here, the head is over here, which is along the y-axis. We have to find its Miller indices. We'll follow the steps. We'll see. First step is that we have to choose the origin onto the direction itself. So I chose this as the origin. So considering this to be the origin, I have to find that, okay, where is my head is going? Head is going along the y-axis. So how many times I have to move along the x-axis? Let's say A is along the x-axis, B is along the y-axis, and C is along the z-axis. So along the x-axis, I have to move by 0 amount. Right? I have not moved anything along this particular direction. I only moved along the y-axis. So I move by the amount of 1. And then along the z-axis, that is C, I again move by 0 amount. So we can write now Miller indices as 0, 1, 0 of this particular direction. Right? Since it's the smallest integer itself, nothing to worry. This is the final answer we have got. Option B is the right answer. Let's move to the next question. How many unit directions does the family 100 represent in the cubic crystal? Okay. So again, see, even if I not wrote about the family, this word, this parenthesis, sorry, this angular bracket itself is sufficient enough to tell that okay, it's a family of direction. So they are representing, okay, this is a family. Tell me which will be the directions which will contribute to this family. Okay, let us say I am someone, and I have some surname. Okay, so they will call, okay, this surname, who are the family. So the first thing is that they are talking about my family, so I should be there to consider. Okay, so first thing, like 100 will be there itself. They are talking about this family, though that person should be there. So we got this. Okay, one we have got. We have to count what else are there. So let's make a cube. This is my x direction, this is my y direction, and this is my z direction. In the cube, I know that a is equals to the b, and it is equals to the c, and also all the angles are 90 degree. So this length, and this length, they all are equal with each other. They all are separated by the same angle, 90 degree. right? And so they all these directions will correspond to a family. So this direction is 100. This direction we just found that 010, and this is 001. So all of them, that is so we got few more. So we can write over here that 010, they have the same they have the same magnitude, they have the same symmetry, they are separated by 90 degree itself. So we'll write them, and then 001. So these three we have found. Is there anything that we are missing which have the same symmetry along, like these things, them same length and all those things? Yeah, there is. So we can see that about the x-axis, just opposite to it, there is a direction. Opposite to the y-axis, this direction, and opposite to the just this direction. All of them are in the same symmetry again. So opposite to the x-axis 100, so we'll just negative it 1 bar 00. Opposite to the y 010, so 01 bar 100 will opposite it. Sorry, 001 will opposite it 001 bar. So again we will write the three things over here. Let me squeeze things. 1 bar 00. Here I will write 01 bar 0, and here I will write 001 bar. So that's how we can say that the total number of directions corresponding to this family are 1, 2, 3, 4, 5, 6, total 6 will correspond over here. Okay, now instead of cube, if it's a tetragonal, what will happen? Keep thinking about that. Let us say I have to find 100, the family of direction which correspond to this particular 100. How I will do that? Keep thinking about this. This thing has been discussed. Sorry, this thing we will discuss in the next upcoming questions. Okay. So keep thinking about the tetragonal. Keep thinking about the orthogonal, orthorhombic cell, unit cell. Those things we will discuss again. So with that, we have solved this question number 3. Let's move to the next question. Fourth one. It is the fill in the blanks type. What determine Miller indices? The coordinate must be reduced to the sorry, I wrote it wrong. When determining the Miller indices, the coordinate must be reduced to the dash integer. We know it should be reduced to the smallest integer. The notation UVW is used to represent a dash of the equivalent direction. So this angular bracket is used to represent the family of the equivalent direction. In the tetragonal system, this 100 family include how many directions along that axis? So now now the time has came for us. Here we saw that 100 for the cubic, all these directions were equivalent with each other, and so we wrote it. Now for the tetragonal, let's discuss. Let me draw one tetragonal unit cell first. In tetragonal, I know that A is equals to the B, but it is not equal to the C. And again, then all the angles are 90 degree. So let's say this is X, this is Y, and this is Z. We know that this and this are equal with each other, but this one is different. And so my this direction 100, this direction 010, and this direction 001. So this direction is having the different length, different dimension, and different symmetry compared to the x and y one. Okay, so these directions, these two x and y are not equivalent with the z, while x and y are equivalent because they have the same magnitude, and if I rotate them by 90 degree, which is about the c axis, I will come to know that okay, about the c axis we know there is a fourfold rotation is there. So about this, if I rotate, x will coincide with the y. And so we got to know that, okay, so this thing is there, like in the direction 1 0 0, I can write 1 0, it will be there, 1 bar 0 0 will be there, sorry, and 0 1 0 will be there. Let's not talk about this right now. Now let's say I am making this square, this thing. I'm making it separately over here. So this is my x-axis, this is my y-axis, and I know that, okay, it's 1 0 0, this is my 0 1 0. There, if I rotate x by 90 degree, I'll get y. Their magnitude have same, exactly same. Now if I rotate y by 90 degree, I should get something that is opposite to the x, right? X dash I can write. So it will be the 1 bar 0 0. Again this direction, that is 0 1 bar 0. It will be there, right? So along with these two will also add up. So we'll write 1 bar 0 0 and 0 1 bar 0. So for the tetragonal, we got to know that there will be total of 4 corresponding to this particular family. Now also you keep on thinking about what about 001. Keep thinking about this. We'll solve it in the upcoming question. So with that we have solved that. Okay, so this will be the total of 4, and they will be along the x-axis and along the y-axis, right? 010, it will be, sorry, 100, it will be along the x and y-axis. Let's move to the next question, fifth one. So here we are having it's very easy. We know the square bracket we use for a single direction. This then angular bracket we use for the family of direction. Then this round bracket we use for the single plane where it is A, and this curly bracket we use for the family of planes. And that's how it is. Every metallurgist, every crystallographer must like this thing. It should be in their mind, or else they won't be able to read any book. Okay, let's move to the next one. Question number 4. Question number 6. Okay, it's a true or false. We'll do one by one. The origin should always be placed on the plane while determining its major indices. See, they are talking about the plane, and we know that origin should not be placed onto the plane. So it's a false. While instead of plane, if it would be the direction, then it will be the true. The reciprocal of intercept are used to determine the Miller indices of the plane. So in the plane we do take the reciprocal, right? That's right. So it's a true. But for the direction we don't take the reciprocal. So instead of the plane, if it will be the direction, then it will be false. In the cubic crystal system, this represents all 6 symmetry related faces. So they are talking about the faces. They are not talking about the direction. And in the cube, this is the family. So again, we just saw that this particular bracket is used for the family of plane. And if you make a cube, the faces of the cube will be surrounded with this particular family itself. That is 100, 010, 001, and then they're negative 1 bar 00, 01 bar 0, and 001 bar. So these things will be there in this particular plane. And all of them, if you draw their planes in the cube, if you make a cube, if you draw these planes, you will find that these are the faces of the cube. And so with that we can say that it's a true. Now the fourth one, A negative Miller indices is represented with a negative sign before the number. So before the number they are telling no, it's not the case. We will use the bar above the number we will use, right? So with that we can say that it's a false. Now the last problem, the last thing is that in a tetragonal system, the horizontal and the vertical faces belong to the same family of the plane. The horizontal and vertical faces are belong to the same family of the plane in the tetragonal. So we draw the tetragonal before. Let me see where it is. Yeah, here it is. So they are talking about the horizontal and the vertical faces. So let's say this is my red one is my horizontal face, and this blue one is vertical face. So they are telling that in the tetragonal the horizontal and the vertical faces belong to the same family of the plane. Will they belong to the same family? Same family means the same symmetry. While we can see that this one is having the fourfold, while this one is the rectangular, right? Because it is a C axis. This axis is C. C is not equivalent with the A. While this is B. B is equivalent with the A. They are equal with each other. They are following the fourfold symmetry. While it is following the twofold symmetry. Their symmetries are different. Since their symmetries are different, they will belong to the different family. So we can say that it's a false. They are not belonging to the same family. They belong to the different family. So with that, question number 6 is over. Let's move ahead. So now, according to the Weismann law, with the direction UVW lie in the plane HKL, what must be the true? So we have saw that it will be the HU plus KV plus LW should be equal to 0. There's a lot of questions, multiple way you can make a questions on this. Internet is like filled with these questions based on the Weismann law. We'll try to solve them also, don't worry. Let's start with this itself. We are having this. Suppose you are given a two plane. Okay, this is a plane number 1. This is a plane number 2. What is the common direction between them? Let us say I am drawing a plane, these things. This is the first plane with the blue one, and this is, let's say this is plane number 2. This is a plane 2, this is a plane 1, and then we are having the common direction. This is a common direction. We need to find the Miller indices of this particular direction. How we can do it? See, Weismann law says that if any direction is lying onto the plane or parallel to the plane, then they will satisfy the Weismann law. We know, since this direction is common to both of them, so the particular, let's say our direction, the common direction is U, V and W. This is the direction which I need to find, and this is the common direction. Now, since it is a common to both of them, then it will satisfy with both of them the Weismann law. So what we have to do? We'll satisfy it with the 1, 2, 3 first, this plane, and then we'll satisfy with the 1 bar 1 1 this plane. Let's go with the first case. So 1 times of U plus 2 times of V plus 3 times of W should be equal to 0. Let's solve it. U plus 2 times of V plus 3 times of W will be equal to 0. So this is the equation 1 we have got. Now let's write about the equation 2, which we will satisfy with this. So it will be the minus of 1 U plus 1 of V plus 1 times of W. It will be equal to 0. So what we can see, that minus of U plus of V plus of W will be equal to 0. This we have got equation 2. There is a 3 variable, but we are having the 2 equations. Again, remember that this is not the absolute value, these are the ratios, so we need to find the only ratio. So let's add them together. In that, what will happen, that the u and minus u will be cancelled out. What we will get, we will get that 3 times of v plus 4 times of w will be equal to 0. So from here we can get the v value. V will be equal to the 4w divided by 3. We got the v value in terms of w. Let's substitute in the equation number 2 itself. We'll try to find the u. So here, from here we can say that if I bring the u on this side, what I will get, v plus w will be equal to the u. Let's substitute the values. What we will get, did I made any mistake? Yeah, it should be minus sign over here. Yes. So now we can write minus of 4 times of w divided by 3 plus of w equal to the u. So now we got the value of u. It will be equal to the minus of w over 3 after solving the above one. So now I need to substitute u, v and w over here. Let's substitute all the values. So I got u as minus of w over 3. I got v as minus of 4w over 3, and I can write w as it is. The common integer w we can remove. What we will get, minus of 1 over 3, minus of 4 over 3 and 1. Now let's multiply everything by 3 itself. So what we will get, minus of 1, minus of 4 and plus of 3. We know in the Miller indices of direction we don't put in the Miller indices we don't put minus before negative. We will put it at the bar, 1 bar, 4 bar and 3. So this is my correct answer. So with that we have solved this question number 8, right? So this is how, like, this is a process which we can do, we can follow. So one more thing, the Weisshorn law is valid for all the 7 crystal systems, so we don't have to worry that okay, we can only apply for the cubic. No, it's not like that. You can apply for the triclinic also, you can apply for monoclinic also. So those things are there. Okay, let's move to the next question, question number 9. Now, see, again, why I am doing this. Again, I give you the 2 planes. Again, I am telling you to find the common direction. Here also, the 2 plane, common direction. We can follow the same procedure. You will follow the same procedure. You will get the same answer, like the right answer here. The one thing is that here the planes are quite complicated little bit. So 1, 2, 3 you have to draw. You cannot draw it like one, even if you draw, but it will be difficult to visualize them. 1 bar, 1, 1. It's easy to draw, but little bit difficult to visualize. So we followed this algebraic method. Now we'll solve this by the geometry. See, since I did not mention anything about the crystal system, which crystal system it is belong to, I will consider any of them. Let us say I am talking about let's say I am considering the cube. Y, X, Z. Now let's draw those planes. So they are talking about the common direction between the 1, 1, 0. This is the plane 1 and 0, 1, 0. 1, 1, 0 will be the, since 0 is on the y and the z coordinate, so it will be parallel to the y and z. So this is the one, the front one, we can say. This plane we are talking about. Now 0, 1, 0, this plane, that is, it is only going to cut the y axis. It's not going to cut any other axis. So we can say that okay, this red plane. So now just by the visualization, okay, itself we can find the common direction. That common direction is nothing but this line. right? And we know that it's going vertically upward. It's going vertically upward along the z direction. So the common direction is 0, 0, 1. That's how we can write. Okay. So see, it's not like always you have to do the complicated algebra. Sometimes just by the visualization also you can get the answer. So these are just two questions which we have solved on the Weismann law. In the upcoming question, we'll see that how else we can use these things. Unmute. Fine. Okay, let me set to save. Let me also turn on the camera. Okay. Reason to save. Okay. Window. Select this one. Yeah, it's visible. This is X-ray. There was some issue on my side, like my PC. I don't know how it suddenly got disconnected. It's turned off everything. Yeah. So, what are the major contribution of the Braggs to the X-ray diffraction studies? So they discovered the X-ray. No, that was not the part of the X-ray. So that was not the part they did. Now they introduced the Bragg's law and interpreting diffraction as a reflection. That is something which we discussed at the start of this particular discussion. That they term diffraction as a reflection, and this is which is very important. Okay, so they invented the X-ray machine. No, they demonstrated the X-ray as are made up of the charged particle. No, that is also not the correct. Yeah, that is right. So we can say that the option B is the right answer over here. Again, let us say someone is asking you, is reflection a diffraction? No. Is diffraction a reflection? Yes. And so diffraction is a reflection. So they termed the diffraction as reflection. You can imagine that diffraction is it can be used as the way of thinking that okay, it is reflecting. Okay. So with that, question number 10 is over. Let's move to the next problem. Okay. Actually, can be. Are these the same questions? Okay, we'll not solve this question. It's somewhat same. Next time I will make question properly. So what is the packing efficiency of the densest possible sphere in the 3D? Okay. So in 3 dimension, what is the maximum packing fraction I can get among this A, B, C, and D? What do you think? Disha, Nukul, anyone? What is the maximum? Yeah, that's right. 74% is the right answer. And 74 we can get in both the cases of hexagonal close pack and also in the case of FCC. Right. And for the BCC, we know that okay, it's 68%. 97% we cannot get in any of the 3 dimension. Only in the 2 dimension we can get, that is the hexagonal packing. Okay. So this is the 2D. While in 3D we can only get 74%. That's how we have solved this question. Now this is a little bit visualization you need to do. What is the coordination number in 2D hexagonal closed pack structure? Okay, they're talking about the 2 dimension. Make a hexagonal pattern. If you got the answer, you can always put it in the comment box. So let us say I'm having this particular, it's 12. This is telling it's 12. So again it's a two dimension. Let's take one of the atom. This one is surrounded by this atom 2, 3, 4, 5, and this 6. So here we can see this particular in the hexagonal one, in the hexagonal closed pack two dimension, we can say that a particular number, a particular atom is surrounded by the total number of 6 atoms. Okay, yeah, nuclear, that's right. So total number of 6, like that is option C is the right answer. Right. So the kissing number or the coordination number here we can say that it's 6. Let's move to the next problem. Now, please answer this question. Okay, it's something which has been discussed in the class. Which of the following is not true? Again, it's not true. About the metallic bonding. So for the metallic bonding, which of them is not true? Are they directional or they? Yeah, that's right. Option A. They are not directional bonds. Right. While in the case of ceramic, like ionic or covalent, we can say they are the directional bonding. While here they are not the directional bond. So and that's the reason why they will always choose to surround themselves by number of atoms as much as possible. Okay. They tend to form they they lead to the formation of the many bonds. That's right. It contributes to the stability of the metal. Yes. More the bonding, more is the stability. And they are not the direction. Always remember that metallic bonds are non-directional. The question number this 14 questions is over. We need to do more 10 questions, and with that we will wrap up the things. Now it's quite interesting, this particular one. It's very easy also, so please try to answer. What about the first one, the packing fraction? Among this A, B, C, D and E, which one it will be? So guys, what about the packing fraction among this? Yeah, these are that's right. Option E, like the fraction of the total volume occupied by the sphere. Perfect. So with that, E is over. The kissing number. What is the kissing number among this A, B, C and D? Among A, B, C and D. Okay, yeah, that's right. Perfect. So the option C is the right answer. Second is C. The maximum number of sphere that a given sphere is touching. Okay. So just now we have seen about that the hexagonal one. Here we saw that okay, this particular atom was touching by a total number of 6 atoms. Right. And then for the hexagonal, what about the hexagonal? Yeah, that's right. It's option D. The stacking pattern in hexagonal is AB type. And then after that cubic we know, right? Cubic is nothing but a ABC packing. Yeah, that's right. Option B is the right answer. So 4 is B. The fifth one is a metallic bond. We just understand that it's a non-directional bond, which is allowing the dense packing. Yeah, Disha, that's right. So for fifth, we can say option A is the right answer. So with that, we have solved this. Now true or false. So we'll hide things. Now we'll go ahead. In one-dimensional closed packing, each sphere is in contact with the 4 other sphere. In one-dimensional closed packing, what is one-dimensional closed packing? This is a one-dimensional closed packing. One-dimensional closed packing, each sphere is in contact with the 4 other sphere. Is it true? Each sphere, let us say first, this is a sphere. False, right? Yeah, that's right. This is perfect. Now the second one. Yeah, that's right. So now for the second one, if we go, the packing efficiency of the two-dimensional hexagonal structure is 90.7%. Yeah, that's true. Perfect. Now let's go to the next question. See, yeah, true. A square packed structure in 2D has the highest packing fraction than a hexagonal close pack. Is it true? The square close pack, they are telling, a square close pack will look something like this. While hexagonal will look like this, the one which we have already saw. Like, okay, let me make it over here itself. Okay, so if you do this part, if you do this study, you will get that no, it's incorrect. Hexagonal is the one which we will get the highest, and so with that we will say that okay, this one is incorrect. It's again a false. Okay, so the square based 2D will not give you the maximum packing. So you can always make a square, make a circle. You can calculate its packing fraction. Okay, so total area of this particular square and divided by the area that is covered by the circle. You will do that and you will get that it will be less than 90. It will be far less than 90. You can take it as a homework that you can do this. You can cross check it. Now the last one. In a closed pack structure, atom can be placed at both B and C positions simultaneously. Simultaneously can be placed. False. That's right. Perfect. So here it's incorrect. False. So with that we have so we can only place either the A. Sorry, we can only place either B, or we can only place either C. Okay, we can follow the A B C A B C stacking, and we can follow the A B A B stacking. But you cannot follow that A B C together. You are doing, then again you are doing A, then again B C. You are putting it's incorrect. The distance between the atoms will not is so small. The distance between the void is so small that you cannot fit A side and the B side, sorry, B side and the C side together, and that's the reason why we won't be able to do this. So with that we have completed with this question. Let's move to the next one. In SCP structure, why can't A and B atom together form a lattice? Okay. Now the reason that why A and B atom cannot together form a lattice, why we are telling that it's a SCP structure, why not the SCP lattice? So the explanation is given in the class. It's so beautifully professor has explained. So they are the two different chemical composition. No, A and B atoms are having the same composition. So this is redundant. Now let's move to the next one. They are not translationally equivalent, right? And this is the reason. See, for anything, if they are not forming the lattice, it's mean that their translation equivalence is destroyed. In the week one also we have discussed that if the translation equivalence is not there, translation symmetry is not there, then they will not form the lattice, and that's what we have observed in this case. Okay, so with that, the B is the right answer. They do not form the close pack. No, this is not something we don't bother about whether they form the close pack or not for the lattice. For simple cubic also we have said that that's a lattice. As long as it is satisfying the translation equivalence, that is sufficient for us. They have different atomic radii. This is also redundant. So with that we have solved this question 70. And also HCP structure is the right name. HCP lattice is not a correct. Okay, I repeated the question. Let's move to the next one. Now from here onwards the things are you will find the similar type of question in the assignment. So the 3-4 plane is parallel to which one? So we are having a particular plane that is 3 4, 7 plane. Among A, B, C and D, this plane is parallel to which of the plane? Okay, can anyone answer this? So here, if I multiply this with any constant and I incorporate that constant like 3k, 4k and 7k, they both will be the parallel. They both will be parallel. This is right, that's right. The option B is the right answer. So this and this, they will be parallel with each other. Now there is one more question. Is only the B or there are more which are the correct? So for the B case, we multiplied with k is equals to the minus 1. So we multiplied with the minus 1 and we got that okay. So it will be the 3 bar, 4 bar and 7 bar. Yeah, that's right. Option C is the right answer. Is there anything more this? Like B and C. In C case, for the B we multiplied with the minus 1. For the C we multiplied with the k equal to 2. Now for the D, we can say k is equals to the minus of 2. Yeah, D with minus 2. That's right, perfect. So here we can say that if I multiply with 2, it will become 6, 8 and 14. For here we can say that if I multiply with the minus of 2, it will be minus 6, minus 8, minus 14. So if you multiply any plane, or even with you are multiplying with any direction, they will be parallel with each other. Okay, so with that we have solved this question. All the member of the symmetry related family of a direction 101. Okay, there is a slight changes. 100 it should be. So the family related directions in the tetragonal unit cell A, B, C and D, among this, which one will it follow? So in the tetragonal, let's draw it. We have discussed it in the, I think, second or third question itself, that there will be some symmetry problem is there in the tetragonal along the C direction. Here A is equals to the B and it is not equal to C. Let us say this is the x-axis, this is the y-axis and this is z. Along the z, there is the elongation is there. So they both are equivalent. This direction and this direction, they are equivalent, while the C direction is not equivalent. So the family, which is 100, 100 is nothing but this one, x direction. So this will be equivalent with the y, that is 0, 1, 0. Right? But it won't be equivalent with the 0, 0, 1. So we will not consider this in this particular family. Is there anything else which we can include in this family? Yes. Opposite to the x, that is 1 bar 0, 0, they will also be having the same dimension. So we'll include them. For this also there will be the 1, 0, 1 bar 0. So we'll include them also. So what is our correct answer? Our correct answer here is that 100 it should be 010 it should be 1 bar 00 and 01 bar 0. This 4. So I think it's there in the option C. Well, if I would have asked you about that 001, then the correct answer will be, for this case, the correct answer will be the B. For this family, this is the right answer. For this family, the right answer is C. Right? And so that's how we have solved this question. Let's move to the next one. Things are repeating now. Okay. Now, sir, can you re-explain? Sir, can you re-explain the 20th question? Yeah, sure. See, in this question, we need to write the family of direction in the tetragonal system, that is one o in this particular direction. That to follow tetragonal. In this we know that A is equal to the B, but it is not equal to C. So if I take, if I make one tetragonal crystal, here it is x-axis, this is y-axis, and this is z-axis. Here we can see that since A is equal to the B, so this length and this length will be equal with each other. While this one is not, this is something different. Okay. So we can say that A and B are equivalent, that is this A and B, they are equivalent with each other, but C is not equivalent. Why? Why it is not equivalent? C is having the length which is different from the A and B. While for the cube, if I draw cube, here A, B and C, all of them are equivalent with each other. They all having the same dimension. They all follow the same symmetry. But here they are not following the C is a problem. And so we can say that the direction, that is A is nothing but 100 direction. B is what? B is 010 direction. So these directions, they are equivalent with each other, but C direction, which is 001, it is not equivalent with these directions. So if I write the family of 100, so the first thing that will come in 100 will be the 100 itself. Now you have to find among these directions is equivalent to what? This is equivalent with this 010. So now let's make this particular base. Let me make this one itself. How it will look like? It will look like a square. Let's say this is my x-axis and this is my y-axis. This direction is 100 and this direction is 010. So what about this direction, the opposite to this x-axis? It will be the 1 bar 00. What about this direction? It will be the 1 bar 0. Right, opposite to the y. So we can say they are also equivalent with each other, right? Their magnitude is also same, and they are also following the same symmetry, that is fourfold. I rotate this x-axis by 90 degree, it will come to the y. I rotate y, it will come to this particular one. Y will come over here, this will come over here, and this will come over here. They all follow the same symmetry, that is 90, and so they will belong to the same family. So here, along with these things 100 and 010, I will also include 01 bar 0, that is correspond to this, and also will include the 1 bar 00. So this 4 will correspond to this particular family. Right? Great. So with that we have solved this question. Now see, this was the cubic, this was the tetragonal. What about the orthorhombic? In orthorhombic, you will feel that A is not equal to B, not equal to C. So in that case, we'll discuss this part. I have one question based on that also. So you just keep thinking on that, what will happen in the orthorhombic. I will place this thing again. Okay, this is over, this is over. 20 seconds. Now Work out the common direction between this and this in the triclinic unit cell. See, now they are asking about the triclinic unit cell. So don't get worried that okay, triclinic unit cell like a not equal to b not equal to c, and all the angles are also different from each other. So don't think all those stuff. We have two planes and we need to find the common direction between them. All we have to do is we have to use the Weismann law. Let the common direction be u, v and w. Do the dot product with 1 1 1. So 1 dot u plus 1 dot v plus 1 dot w will be equal to 0. Again, we did this, we got the first equation that u plus v plus w is equals to 0, equation number 1. Now what we will do, we'll do the same thing with the O1. So 0 times u plus 0 times v plus 1 times w is equal to 0. So from here what we have got, that is w is equal to 0. So this is equation 2. Substitute this in equation 1, what you will get, u plus v plus w, which is 0, is equal to 0. So u is equal to the minus of v. Now let's substitute the thing which we are aware now in this direction, that is, okay, I should write this in the box, it's only 1 right now. So in the place of u I will write minus of v, in the place of v I will write v, and in the place of w I will write 0. The common factor all of them is having that v. 0 will always contain v. So it will be minus 1, 1, 0. This is how we can write, but again it's not 100% correct yet. We have to put bar, 1 bar, we have to put it above. So this is our correct direction. So in for the triclinic system, even for the triclinic unit cell, such complicated unit cell, we'll get that okay, in the similar step, in the similar manner, if we follow the Weismann law, we will get the answer. Okay. So whether it's monoclinic, triclinic, cubic, you can apply these things to all. And let me tell you one more thing. In the gate question, in the gate metallurgy, you will find the similar type of question. 2-3 times it has been repeated. Okay. 20 seconds is over. 22. Now, this is very interesting question, and it is somewhat similar to your assignment question. I made it little extra complicated. See, I cannot solve that question itself, the assignment question itself. So I have to modify it, and so we can now discuss this. And the assignment question, you will feel that is comparatively it will be easy for you. What is the Miller indices of a plane that make an intercept of 1 angstrom, 4 angstrom, and 8 angstrom with A, B, and C axis, respectively, in orthogonal crystal, with C equal to 2 times of A equal to 4 times of, sorry, C equal to 2 times of A equal to 4 times of A. 2 times of B it should be. Yeah, 2 times of B and 4 times of A. We need to find, see, we are having the axis, we are having the x-axis, A, B, and C. Okay, we are having some plane, I don't know this plane is what, like, but they are telling that it is intercept at, for the x-axis it intercept at 1 angstrom, for the y-axis it is intercepting at 4 angstrom, and for the C, that is z-axis, that is 8 angstrom. Now we have to do, what we have to do is we have to write the Miller indices. See, for Miller indices we know, we write something like, okay, something is in the terms of A, B, and C we write, right? How many times of A, how many times of B, and how many times of C, that is what we write, some number. So for example, 1 1 1 direction in the cube, how we will write, we'll write 1 times of A, 1 times of B and 1 times of C, not plus sign. And from there then we'll remove this A, B and C. Okay. So now we have to write these things in terms of A, B and C. This intercepts while they are giving in terms of the Armstrong. So let us assume something. Let us assume that our A axis is 1 Armstrong. A axis is 1 Armstrong. So what we can write, their intercept was 1 Armstrong along the A, along the B it was 4, and along the C it was 8 Armstrong. Now we have assumed that 1 Armstrong is nothing but a first one, A. So now we will write only the magnitude, 1 times of A, 4 times of A, and 8 times of A. We know something. See, for the A is not a problem, that is 1A. For the B it's a problem. We cannot represent in the A terms. We have to represent in the B terms. So what we can say, see, we know that C is equal to the 2 times of B is equal to the 2 times of A. Sorry, 4 times of A. So 2B is equal to the 4 times of A. So we got to know that 4 of A is nothing but 2B. 4 of A is nothing but 2B. We got this. What about 8 of A? We have to represent 8 of A in terms of C. So 4 of A is equal to the C. So 8 of A will be equal to the 2 times of C. Right? So now we represented this intercept in term of A, B and C. So now we can write the mirror indices as again it's a plane. So we got that A, that is 2, 2 and 2 we've got. Now we have to take the reciprocal, 1 upon 1, 1 over 2, 1 over 2. We got this. We will convert this to the nearest smallest integer. We will take the, okay, we got that, okay, 2 is a common factor in the denominator. We'll multiply everything by 2. So we'll get 2, 1, 1. This is the one. Okay. So our main aim is to get this. We have to represent all the intercepts in terms of A, B and C. Their different crystallographic basis vector. Okay. So with that we have solved. We did one assumption. We did assumption that, okay, we consider 1 Armstrong to be the A. You can also consider 2 Armstrong to be the A. It won't change anything. It's just that the mathematics will get little bit evolved, but everything will remain and end result you will get same. So that's how we have solved. So student might get sometime what mistake they do, and among the options there will be the option which will be like, if they follow that mistake they will get the right answer also. So what they will do, they will, okay, 1 Armstrong, 4 Armstrong, 8 Armstrong, let's take the value 1, 1 over 4, 1 over 8, and now they will just do the common factor from this, which is incorrect. We have to first get to the A, B and C. We have to represent these intercepts in terms of A, B and C, then only we should proceed. Okay, so that's how we have solved this question number 23. If there is any doubt, let me know. If not, we'll move ahead. Okay, now I only have the 2 questions. We'll finish it up and then we can wrap up the things. So now what I was telling you guys about the orthorhombic crystal. The symmetry related family OO1 can be represented by what? So in the orthorhombic system, we have to represent OO1, this particular family. Let's draw it. We know that in orthorhombic that A is not equal to B, which is not equal to C. So all of them are not equivalent with each other. So let's draw one. Where this and this are different, all 3 are different from each other. So this direction OO1 is this one. So the first thing we know that this direction will be included in the family itself. Okay, if someone is talking about my family, I should be included first, then they will talk about the remaining members. So I'm over here. Now the other things, can I write O1 O in this particular family? No, their lengths are different, their symmetry doesn't match. What about 1O? Again, the length are different, the symmetry doesn't match also, right? So this will not be included. Again, what we will include over here, will include the opposite of this, that is O, O, 1 bar. So in this family, only two members will be there, and those two members are O01 and O01 bar. That is option B is the right answer. So you can see now that how the things are changing. So not only for O10, even if I am talking about 100, this particular family, how we will write? First 100 will be remain as it is, like that is this one, and the opposite of it will be there, that is 1 bar 00. So the things are changing drastically. See, where is that particular figure? Yeah. So for the cubic, all six, that is this direction, this, and their opposite will be there. For the tetragonal, we got to the 4, like only this will be there. But for the orthorhombic, we got to the 2. So that the way the symmetry are changing, the direction, the family is also getting reduced. The size of the family is getting reduced. So 24 is, that's how we have solved it. Any doubt, let me know. Okay, let's move to the next question if there is no. Now, I took this question just because a similar question was there in the assignments. The direction that bisect the plane normal, this and this, in the cube. So they specified one thing, that it's a cube. What they are telling, the question is that we are having the two plane. These two plane, and the direction that bisect the plane normal. So there is a plane normal. Let's say this one is a plane normal to the black one. This is a plane normal to the blue one. Okay, so we'll write N2 and 1. Now these two normals are there. Let's say I'm drawing in the different space now. For that, they are telling that there is the direction that bisect the plane normal. So we have to bisect it. This is bisecting. So what we can say, since it is bisecting, their angle will be equal with each other. We have to find the Miller indices of this, the one which is bisecting. How will we proceed this? We are having the two plane. Their indices are given. The indices of the planes are given. And to that plane we are having the normal. And that normal, those two normal, the angle between them is getting bisected by the one vector. And we have to find the Miller indices of that vector. Okay, it's very easy. Since we know the indices of the plane and we know that it's a cubic, the one result we have got, that HKL plane for the cube is perpendicular to the HKL direction. So for a particular plane, that is, let's say blue one, which is representing the 111 bar, this plane, its normal will have the same indices, 111 bar. So the normal of this also, the black one, will be having the same indices as the plane, that is 111. I should write the square bracket. So I found the Miller indices of both the direction, both the normal 111 and N2, which is 111 bar. See, now we can easily do this. we are having two vectors. We need to find which is in the between of them. Right? There is something we have learned about the vector addition. If we add them, we'll get the bisector itself. It's symmetrically, right? So now let's add the similar indices. 1, 1, 1 bar and 1, 1, 1. What we will get? Let's add them. This will be 2, this will be 2, this will be 0. So this is the direction which is bisecting both the normals. We can simplify it further that okay, it will be the smallest integer is 2. We can, like, the common factor is 2, we can take them 1, 1, 1. So this plane 1, 1, 1 and 1, 1, 1 bar, the normal of them is getting bisected by this particular direction. So now again you will see that the if you try to visualize it geometrically, it will be very complicated to do. Still, but give a try. While if you do algebra, it's very easy. All we have to do is okay, we have to find their plane normal, and for the cube it's very easy. For the cube it will be like whatever the plane indices is given, then normal will have the same indices, and this is only true for the cube, not for anything else, not for the tetragonal or monoclinic orthorhombic, those things, no. Only for the cube. And once you find the normal, the indices of them, you can add them. It's a direction, you can add the directions. So with that we have solved this question number 25. Am I having anything more? No, that's all. So with that we are done with today's class, today doubt solving session. Please let me know if there is any doubt in this particular entire doubt solving session you have faced. If yes, we can discuss them. If no, then we will conclude our session here. Or if you find any problem, anything like something which you have not got in the class, if you have any doubt in that, we can discuss them also. Okay, since there is no doubt, let's conclude our today's session. And with that, please try to solve your assignment questions, and just to update that week 1 assignment is been like you can submit it till the 5th of Feb. So if you have not solved it till now, please do that, and we can discuss those assignment in the next week once the answer is come out. Okay, till then I cannot discuss those things. And also for the week 2 the assignment has been already floated, so you can go through this. Please submit those also if you want to appear for the exam. Even if not, then just do it for the practice. The similar question you will get in the gate also. Okay guys, with that we can conclude today's session.
Good afternoon, sir.
Yeah, good afternoon.
Sir, I just had one query. For the exam, is it the notes are sufficient or should we go for some other book also?
So for this particular course, the exam, you will mostly see that the questions are from the assignments, majority. And also if they are not from the assignment, they will be 100% sure that they will be from the course itself. So you don't have to refer any book. Just have to go through the entire content of this particular course.
Okay, sir. Got it. Thank you, sir.
Yeah, sure. Okay guys, since there is no any doubt, so we can conclude our session. Okay, bye bye.